Okay, welcome everyone. Welcome to the last lecture of the Supersymmetry mini course. And again, we are very happy to have Professor Silvia Penati to give us this wonderful lecture series. And please take the conference. Thank you.
Thank you very much. Thank you for being here also for the last lecture. Okay, so what I'm going to do today in order to wrap up a little bit the whole discussion is to somehow exploit the powerful tool of Superspace in particular that we introduced in order to discuss some physical implications of supersymmetry. We started already last time at the very end of the previous lecture introducing the simplest model, which is called the Vezzomino model. So now we are going back to discuss more about the Vezzomino model. Then I will introduce a little bit of super Young Mills, or at least in the, let's say, in the super gauge in the abelian case. If I have time, I can move to non-abelian case too, and see at that point, just a brief summary of which are the main physical properties of quantum super Young Mills theories. Okay, but before starting, I remember the last time somebody asked me about the possibility to formulate in superspace or the supercalculus, introducing superforms, blah, blah, blah. The answer is yes, and I promise to give you some reference. And in fact, here I am. So basically, if you want to develop supercalculus in superfields, in superspace, you should rely on the whole mathematical construction of supermanifolds. Where you can develop, differential calculus, integral calculus, form, which are called superforms. Okay, I can give you a very short list of references, but they are pretty good. Well, first of all, if you want to have just a little introduction to superforms, you may have a look to the book Superspace, the one that I mentioned at the very beginning, Superspace and 1000, blah, 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 by Gates, Crisaro, Rocek, Siegel. I can even tell you what page. If you go to page 181, you will find a brief introduction to superforms. But if you want to go deeper inside the subject, you can look for the book by Bryce DeWitt, which is called Supermanifolds. Okay. And then, as usual, there is a beautiful paper by Witten. This is notes on supermanifolds and integration. And this is oh, this is already archived. $199. Okay. Okay, as promised, let's go back discussing the Vezzomino model. So I will rewrite the action in superspace, and I told you to do the exercise. I don't know if somebody tried to go to components. So the Vezzomino model, the simplest version of the Vezzomino model, describes the propagation of one single chiral superfield. One chiral superfield phi and the complex conjugate phi bar. In a more general setup, you can also define the Zumino models describing propagation of more than one chiral superfield, but that's fit to the case of one single chiral superfield. And the action in superspace is 1/4 the integral. Remember my notation. When I write something like this 8z, I mean the usual 4-dimensional integration times the Berezin integration over theta and theta bar. Okay. And this is the kinetic term written as phi bar. And then we have the superpotential part, which is the integral in d6z of 1/2 m phi square plus lambda over 3 factorial phi cube, plus the complex conjugate, which means the d6z bar 1/2 m bar phi bar square plus lambda bar over 3 factorial phi bar cube. Okay, and still remember that when I write d6, I mean a chiral integral, which is d4x d2 theta. And when I write d6z bar, this is an anti-chiral integral. So I have d4x d2 theta bar. Okay, this is just notation. Okay, I told you, to do the exercise to go to components. So now you go to components. I taught you last time how to do that. Hopefully you remember. Of course, in terms of components, the superfield contains a scalar, a complex scalar, psi alpha, which is the left part of the Majorana fermion, and another complex scalar, and phi bar, of course, contains the complex conjugates. Okay. If you reduce your action in components, you will obtain the following. Reducing in components, even if now you don't remember exactly how to do it, but the point is that basically what we are doing is to integrate in theta theta bar, okay? If you take, for instance, this term, you integrate in theta theta bar, you remember that the Berezin integration is equal to derivatives. So integrating over theta theta bar is equivalent to apply d squared, d bar square, where d are the spinorial derivatives, and then you evaluate everything at theta and theta bar equal to 0. And what you will find is a polynomial here in terms of the components, and this is your action in components. Okay, so if you do that for the free part is, this one, the non-chiral part, you will obtain d4x minus phi bar box phi minus I over 2 psi bar alpha dot d alpha alpha dot psi alpha plus 1/4 f at bar. This is the free part. Whereas from the superpotential, you obtain minus m phi f plus m over 2 psi alpha minus lambda over 2 phi square f plus lambda phi psi alpha plus the admission conjugate. Okay. Okay, but this level, I'm not happy enough, not yet, because I still have into the game these auxiliary fields. Remember, F and F bar are auxiliary fields because there is no kinetic term for this for these fields. Therefore, what I can immediately do is to write down the equations of motion for the auxiliaries and eliminate F and F bar from S by replacing F and F bar with their equations of motion. In fact, if I consider the equations of motion for, let's start for F, so you vary respect to F, okay, what you will get, now let's do first F bar. I vary respect to, sorry, Let's do for f. I vary respect to f, so what I get is 1/4 f bar from this term, okay? From this term, I get minus my m phi, period. Then I obtain another contribution from here, which is phi square, period. And this has to be equal to 0. Okay, therefore, f bar is 4 m phi plus 2 lambda phi square. You should now do the equations of motion for f bar, but you can even avoid doing it. It's just a question to take the complex conjugate of this equation, and you will find that f is equal to 4 m bar phi bar plus 2 lambda bar phi bar squared. Okay, so what you have to do now, wherever you find f, you replace f with this expression. Wherever you find f bar, you replace f bar with this expression, okay? So replace f in bar in S with their equations of motion. You eventually find an action which describes the propagation of physical degrees of freedom of your chiral superfield, because now we have eliminated the auxiliaries. And if you do the calculation, I keep telling you, do it. So let me write here. Do it. Do it. Okay. This second do it is trivial algebra. So you will find the following action, which is minus phi box phi bar. I'm not going to touch the kinetic part, of course. Okay. But now I have plus m over 2 psi alpha plus m bar over 2 psi bar alpha dot which may be interpreted as mass terms for the fermions. Then we have minus 4 m squared phi bar, and this is a mass term for the scalar, minus 2 m lambda phi bar square plus phi bar square phi square. Okay, what I'm doing here is to take lambda bar equals to lambda to simplify the expression. Okay. Minus lambda square phi bar square plus lambda phi psi alpha plus lambda phi bar alpha dot Okay, this is something quite interesting because, first of all, as already announced last time, I, apart from the free part of the action, which describes at this point the propagation of a scale, complex scale, massive complex scalar and a massive Majorana, okay, if you set m equal to m bar. Let's have a look at the interaction terms. In the interaction terms, first of all, I find this beautiful phi square, phi bar square, which is nothing but the usual phi to the 4 interaction for a complex scalar that probably you have studied already in ordinary quantum field theory, plus extra terms which involve the interaction, well, this, sorry, there is a misprint here. It should be phi bar. Okay, there is also a cubic interaction, but what is also interesting is that there is sort of Bicocca interaction between the scalar and the fermions. That's why the Wedge-Ziminovic model is also considered the supersymmetry version of lambda phi to the 4 theory. Okay, so this is the SUSY version of the usual lambda phi to the 4. In particular, if we draw, the Feynman rules, okay, will involve writing down the propagators that you can read from the free action. But let's focus in particular on the some kind of interactions. So interaction vertices. As I said, we have a lambda phi to the 4 for a complex, but we also have cubic interactions of the form phi bar, and the complex conjugate, phi bar, phi. And then, as I said, Yukawa interactions of the form phi bar, and the complex conjugate, phi bar, psi bar. Okay. Good. At this point, we can think of quantizing the theory. How do you do in general for supersymmetric theories? You can quantize, and we will think quantizing the theories, because what I want to do today, as I said, is just to give you an overview of important physical properties of quantum supersymmetric theories. So if we quantize the system, we can do it using functional methods. It means that I'm going to define a generating functional. Let me call it this way, which is nothing but, up to a normalization factor, the functional integral over the superfields. I'm now integrating over superfields, not simple fields, e to the I, the action that I wrote above, which is a function of the superfields, written in terms of superfields. So you can really work with the action, this one, written in superspace. You don't have to go necessarily to components, okay? And then, as usual, we add source terms for phi and phi bar, which corresponds to j and j bar, and this will be the integral of this is a chiral integral of j phi plus an anti-chiral integral of j bar phi bar, okay, where j and j bar are still chiral and anti-chiral fields. So d bar alpha dot j is equal to 0 and d alpha j bar is equal to 0. That's why these are chiral and anti-chiral integrals, respectively. Okay, and then you start building up, you can use these interaction vertices that your theory provides you. You know how to compute, you have to learn how to compute propagators in superspace, and you build up sort of super Feynman calculus. Which means that you can organize your perturbative expansion. You may think of perturbing, performing perturbative expansion in the coupling constant lambda, if lambda is sufficiently small. It means that the perturbative expansion of the functional one, this one, can be organized in terms of what people call supergraphs. These are nothing but, kind of Feynman diagrams, but where, the vertices are interaction vertices between superfields, and the propagator are superpropagators. I cannot enter into any detail about that, so just believe me that if you really want to do some perturbative calculation concerning n equal to 1 theories in 4 dimensions, using the techniques of supergraphs is definitely the best way to do it. And if you are interested in doing this kind of calculation, you can still look at the book Superspace. So look at Gates, Grisaro, Project, Seeger's book. Okay. Just take it for granted, okay? You can use this, powerful technique. And what you find studying the Vezzomino model at quantum level is the appearance of first very interesting property, which goes under the non-renormalization theorem. Okay, and this holds not only for this particular model, non-renormalization theorem holds for a generic action for chiral superfield of the form we have a non-chiral integral of some, remember, Kähler potential, which is a function of phi bar, plus a chiral integral of what we call the super potential, plus the complex conjugate. Of course, the Vezzomino model that we are considering now is a particular example of this kind of sigma models, after all, where you choose the Kähler potential to be the simplest one, simplified phi bar, and we have chosen W to be at most cubic to be a polynomial at most cubic in phi bar. Okay. What is this non-renormalization theorem, which is the statement? Okay, the statement is that there is no renormalization of W and W bar. So the superpotential does not renormalize. And this is the power of supersymmetry. This is a powerful consequences of supersymmetry. What does it mean? It means that when you start doing perturbative calculations, you will find out that while you actually produce ultraviolet divergent terms contributing to the Kähler potential, you will never produce ultraviolet divergent contributions contributing to W and W bar. How do you distinguish to which part of the action ultraviolet divergences correspond to? Well, it's very easy. The Kähler potential is featured by a non-chiral integral. This is a complete supermanifold integral, whereas the superpotential comes with a chiral integral, okay? Here you have a d2 theta bar. Here you only have d2 theta, and here you only have d2 theta bar. Okay, doing perturbative calculations, one immediately realizes that the way superspace organizes your Feynman integrals corresponding to your Feynman graphs, you will never produce divergent terms which are proportional to a chiral integral, d6z or d6 zeta bar. The only possibility for you, when in the calculation you produce ultraviolet divergences, is to always produce a non-chiral integral. Therefore, all the ultraviolet contributions can be reabsorbed in a renormalization of the Kähler potential, whereas W and W bar do not renormalize. This is the content of the no-renormalization theorem that you can even summarizing still the chiral integrals in the action never renormalize, never get divergent contributions. There is a proof of this non-renormalization theorem, which goes back to, again, Grisaru, Rocek, and Siegel, which is based indeed on the supergraph techniques. Okay, I'm not going to give you the proof, of course. So there is a perturbative proof of the theorem. This is, so basically this comes from, supergraphs properties. And this was given the beginning of the supersymmetry history by Grisaru, Rocek, Siegel. Okay, but this is not completely satisfactory because this is a perturbative proof. So as long as you are attaching the problem of computing quantum corrections to your theory perturbatively, okay, that's perfectly fine. But it might be, that when you consider, you start putting into the game also non-perturbative corrections because they are no longer working for lambda small, for instance, in our Vezzomino model, then it might be that, some non-perturbative corrections to the superpotential appear. So in order to prove that even non-perturbatively W does not renormalize, so the theorem is still true also non-perturbatively, you have to rely on still the power of supersymmetry, which eventually implies what people call holomorphicity, depends your taste. Okay, and this is based on a nice argument given by Seiberg, so non-perturbative proof. This is a perturbative proof based on holomorphy of W phi. I will explain what I mean with that, and the argument that I'm going to present is due to Seiberg. And you can find it in 94.08013 and 93.09335. Okay, so in order to give you the argument, let's focus again on the Vezzomino case. So let's take W to be m over 2 phi squared plus lambda over 3 factorial phi cube. Okay, now the original observation due to Seiberg is the following. We can, here we have the superpotential, which is a function of the superfield phi and two scalar couplings m and lambda. But at this level, I can think of m and lambda to be the lowest component of a superfield, which has the rest of the components equal to 0. Okay, let me write something, maybe it will be more clear. So we promote m and lambda to be chiral superfields of the form well, let's change letter. Let me call this m, becomes m plus, remember, then I should have a theta term, but this is 0, plus a theta squared term, but this is still 0. Okay. And the coupling constant becomes lambda plus, again, 0 components in the higher terms in theta. Okay, therefore, at this point, my superpotential is a function of 3 superfields, chiral superfields, But the main point is that this is a function of only, you know, phi, m, and lambda. It is not a function of m bar, lambda bar, and phi bar. This is the holomorphy of W. So this is holomorphic in m, lambda, and phi, in the sense that it does not depend on m bar, lambda bar, and phi bar. Okay. Good. This is the first observation, which relies on holomorphicity of W. And in fact, this, let's say, the fact that the superpotential is holomorphic is strictly imposed by supersymmetry. Okay. Now, I cannot tell you more than that, but believe me, supersymmetry implies W to be holomorphic. Okay, this is the first observation. The second observation is that once I have written W in terms of three superfields, I can observe that the assign suitable R charge to these superfields and introducing another U1 under which these three superfields are charged, I can constrain the structure of W even more. I'm going to tell you why. So if I look at this particular choice that we made for W, you immediately realize that if I take, let's do the following table. Let me call this U1 symmetries. And let me do the following table. Let me take U1 R symmetry, okay? And another U1 that I invent, rigid U1, okay? Let me put here the three chiral superfields. Remember, in terms of U1 symmetry, if I want the superpotential part of the action to be R symmetry invariant, remember that the total R symmetry of W has to be 2. This is something that we mentioned last time, because, you know, the measure d theta brings -1, but you have d to theta, so the measure will bring a total R symmetry charge, which is -2. In order to compensate this -2, W has to have R symmetry 2, okay? Therefore, you can immediately see that, you know, these two terms are okay. If you assign R symmetry 1 to phi, you assign R symmetry 0 to M, and in fact, the first term will have R symmetry, in total, we have R symmetry 2, fine. And then we assign R symmetry -1 to lambda, because then we have 3 - 1, 2. And this is perfectly fine, okay? Moreover, I immediately realized that there is another U1, which leaves the integral of W invariant, which has nothing to do with our symmetry. So this is a U1 symmetry under which only phi, m, and lambda are charged, not theta or d theta, okay? This does not touch theta and d theta. If you assign U1 charge 1 to phi, -2 to m, and -3 to lambda, you will immediately see that, you know, see what happens. Here I get 2, -2, 0, fine, because the measure this time does not carry any U1 charge. And here we get 1 times 3, which is 3, -3, 0, perfect. Okay, so pay attention that, let me write also this one, this way, this is -3. D theta here has dimension, sorry, has R symmetry -1, here has U1, 0. Okay, for sure, this these two U1 let's say these two U1 with these two U1 assignments, these two U1s are two symmetries, are two U1 global symmetries of my original action, of my Vertzumino action. In fact, as I have just proved, W is perfect. What about the kinetic term? The kinetic term, remember, is phi bar, but of course, if phi has U1 charge 1, phi bar has U1 charge -1, therefore they compensate, and the same thing happens for the other U1. Okay, so the Vertzumino action has these two U1 symmetries. Vertzumino action has these two U1 symmetries. Okay, now let's go to the quantum version of the theory. So now I quantize the theory. I build up the functional integral, the effective action. Actually, I have to look at the Wilsonian effective action. Of Vertzumino model. Okay. Okay, if I look at the Wilsonian effective action, and you know, it is reasonable to assume that at quantum level, these two U1 symmetries are not broken. And it is more than reasonable to assume that supersymmetry is not broken at quantum level. We have to require that, you know, when I compute the effective superpotential, the effective superpotential has to be holomorphic. Otherwise, I'm going to break supersymmetry, and has to be U1 are symmetry and U1 invariant. Okay, good. But with this kind of assignment for the U1 charges, you immediately realize that these conditions, these, let's say 2 or 3 conditions, imply that W, the effective superpotential, which will be, first of all, it will be only a function of m, lambda, and phi because of the holomorphy of the superpotential. Okay, and in order to respect the assignment of the U1 charges, it can be necessarily, and cannot be anything like that, n phi squared times a function of lambda phi over m. Okay, because if you go back to the assignment, you will immediately see that this is the only possible combination of lambda phi and m in order to have something which has R symmetry 2 and the other U1 0. Let's assume that f is a smooth function, generic for the time being, smooth function. Okay, therefore, if it is a smooth function, I can expand f in powers. So I can write this as an expansion, an of lambda phi over m power n. And let me rewrite this in a better way. This is the sum, okay, from 0 to infinity of an, then I have lambda n phi power n plus 2 divided by m n minus 1. Okay, this is already a very good piece of information because, you know, using symmetries and the holomorphy of the effective potential, I already know which can be the most general structure for my quantum superpotential. But this is not the end of the story, because at this point, I'm going to require to somehow to constrain this expression by, you know, two reasonable requirements, two extra requirements. Which are the following. The first one, we want, because this is, as I said, a definitely reasonable requirement, we want that for lambda going to 0 and m going to 0, we recover the free massless case, where nothing changes and W is the usual one, okay? Which is 0. So for, if I send, so asking that for lambda going to 0 and n going to 0, we recover the free massless model. Okay. We obtain a condition on these coefficients because, of course, for n going to 0, this has to go to 0. So n has to be, of course, as I already wrote here, greater or equal to 0. But the main point is here, you know, if n is equal to 0, okay. Yes, if n is equal to 0, sorry, if n minus 1 is greater than 0, definitely greater than 0, you do have 1 over m powers, which means that your expression becomes a singular when you take the limit m to 0. I don't want that. Therefore, in order to have a smooth limit for m going to 0, we need to require that n can only be 0 or at most 1, which means that all the coefficients an are equal to 0 for n greater or equal to 2. Okay, therefore, from here, I read that my effective superpotential will be given only by the sum of two terms, the one corresponding to n equal to 0 and the one corresponding to n equal to 1. But for n equal to 0, we simply obtain a0 phi square m, a0 m phi square. There is an m from here. And for n equal to 1, we get a1 lambda phi cube. Okay. Second requirement, W, the quantum W, we want to be, has to be related perturbatively to the classical superpotential. Okay, since m and lambda are already the parameters, the chiral superfields which appear in the classical superpotential, this implies necessarily that your effective superpotential is eventually given by m over 2 phi square plus lambda, lambda, big lambda, over 3 factorial phi cube, which is the classical potential, superpotential. Therefore, there are no corrections not even non-perturbatively. No quantum corrections. And I insist, it is definitely very nice to see how powerful is the supersymmetry, because supersymmetry, as I said, implies holomorphy. Holomorphy is basically the main character of this proof, together with, of course, the obvious assumptions about connection with perturbative calculations, plus symmetries, as usual. This is something that you know already. In general, symmetries are very powerful in constraining the structure of quantum theories. But here you can see that, you know, supersymmetry also plays a similar role. Okay, so what is the conclusion concerning our, let's say, generic, at this point I can go back to our generic model of this form. I don't have necessarily to relate to the Bezzumino superpotential, okay? I don't know, probably I should give a number here. Okay, so let's say conclusion. Going back to model 2. Okay, we find that perturbatively the quantum action, effective action, will be of the form, let me call it gamma, in integral. Let's stick to the superspace notation. So I should not write this, but I should write this. Okay, times what? Times the, you know, the classical contribution plus suppose that we do calculations, for instance, in dimensional regularization, you will have some 1 over epsilon divergence plus 1 over epsilon square, blah, 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 blah. Okay, but you never produce this kind of corrections to W. Okay, so what you have to do, of course, at this point, you have to absorb these divergences by a multiplicatory normalization of your superfields. Okay, so divergence UV divergences are renormalized by setting phi renormalized equal to Z phi power 1/2 phi, the usual expression that you write also in ordinary quantum field theory, except that now phi is a superfield. So when I make this statement, it means that all the components of the superfield renormalize the same way. Okay, because if you think of expanding in components, the left and the right hand sides, you will see that this Z enters the same way in all the components. Okay. Then what I typically write, of course, is that I will have to deal with some, let me call it ZMM, and then I have to deal with some Z lambda lambda. However, from the no-renormalization theorem, what I get is that M phi square has to be equal to N renormalized phi renormalized square, and lambda phi cube has to be equal to lambda renormalized phi renormalized cube. Okay, and therefore you will end up with Zm times Z phi, which has to be 1, and Z lambda times Z phi power 3/2 has to be 1, which implies that, you know, there is a non-trivial renormalization of the coupling constant, the mass and the lambda, but these are driven by the renormalization of the field function of the superfield. In fact, what I find is that Zm is nothing but Z phi minus 1, and Z lambda is Z phi power minus 3/2. Okay. What happens is that, you know, in this kind of theories, so we are dealing, remember, n equal to 1, supersymmetry, what happens is that in general, you will get corrections to the Kähler potential, which in our case, I should not, sorry. If I stick to 2, actually I should be more general here and write this as, you know, the generic Kähler potential. Okay, in general, you may have, you know, correction at any order in perturbation theory, and therefore you will produce a non-trivial renormalization functions, in particular non-trivial renormalization function for the coupling constant lambda, which then will be featured by some beta function. And there is a natural running, lambda is a running coupling according to the usual setup that you hopefully know in ordinary quantum field theory. Okay. Maybe if you have question, you can ask when we stop for the break. Let me say still a few more things about this kind of models. In particular, I want still to discuss kind of models where you do not necessarily fix the superpotential. Let's keep the superpotential as W with no specific expressions for W. What I want to study in this particular setup are general conditions for SUSY spontaneous symmetry breaking. Okay, remember that I told you at the very beginning of this course that we have a very strong condition. Wait a sec. Yes, it does. Yes, there is all, yeah, you may have, the question is whether Kähler potential has any relation with Kähler manifold. Yes. There is also a geometric interpretation of SUSY theories written in terms of for chiral superfields. Yes. I was mentioning, yes, that at the beginning of the course, I told you that one necessary and sufficient condition to have SUSY preserved at quantum level is that the potential, the scalar potential, the bosonic potential and potential energy is always positive or at most 0, remember? Okay, so I want to translate this generic condition that we basically infer from the algebra. I want to realize it in a more specific way in this kind of models. Therefore, I will still be considering this particular kinetic term, but I will keep the superpotential generic. Okay. Okay, so what I want to compute is the potential. My question is the bosonic potential. Okay, in order to find out the bosonic potential, I have basically to reduce in components the superpotential part, because remember, this is just the kinetic term. So the potential comes from the superpotential. So we reduce the integral of W in components. Okay, setting fermions to 0. It means that whenever we produce something which is the alpha phi evaluated and d bar alpha dot phi bar evaluated, these are set to 0 because you don't have you do not have background values for fermions, only for scalars. For bosons, let's see what happens. So let's consider, for instance, this one. Remember that by definition, this is the 4-dimensional integral times d square applied to W evaluated. Okay, but let's do the calculation. This means the integral 1/2 d alpha, this is my definition of d square, applied to W, evaluated. But this is the integral of 1/2 d alpha. Now, if I want to apply d alpha to W, I will write this as the derivative of W respect to phi times d alpha phi evaluated. Okay, good. Now you could have two possibilities. One is applying the d to the first factor and then d to the second factor. When I apply the d to the first factor, I produce fermionic terms, which are in fact 0 because of my setting. Therefore, the only possibility is when d hits the alpha phi. And so eventually this is nothing but the integral of the derivative of W respect to phi times d square phi evaluated, okay, which is eventually the integral of dW respect to phi evaluated at theta equal to 0 times, remember, when I evaluate d square phi at theta bar equal to 0, this is, according to our conventions, equal to minus f, the last components of the superfield. Okay. You do the same for the complex conjugate. So to summarize, what we get is that d6z w phi will give you a contribution which is minus the integral d for x dw over d phi times f. If you take the complex conjugate, you will produce minus the integral d w bar over d phi bar times f bar. If you consider the kinetic term, remember that this produces in our conventions, okay, forget about the 1/4 f bar, the integral of f bar. Okay, good. So if you put everything together from your action, I will get a lot of other terms, but let me focus on the f bar terms. You will get the integral of f bar minus derivative of W times f minus derivative of W bar times f bar. Okay, but remember that f and f bar are, as you can see also from these expressions, are auxiliary fields. So what I can do is to eliminate the auxiliary fields using their equations of motion. So the equations of motion for f and f bar can be easily found out varying respect to f and f bar. So what you get is that f is equal to the derivative of W bar and F bar is the derivative of phi. Now you replace, and from your action, you obtain a term which is minus the integral of dw over phi evaluated, which will be a function only of small phi, times dw bar over phi bar evaluated. Okay, which you can even want to rewrite as F bar. Very good. This is the potential. So by definition, this is minus the integral d for x of the potential energy, which is now is a function of the lowest components, phi and phi bar. Okay, therefore, what we have found is that in this specific set of models, these are describing the propagation of chiral superfields, the potential energy is given by the derivative of the superpotential evaluated times the complex conjugate. Okay, you can even write this as the modulo of the dw over d phi square. And we know that in order to have, well, first of all, in order to preserve supersymmetry, this has to be greater or equal to 0. And if we find what we call the vacuum state, which is the lowest energy state, let me call phi 0, such that d of phi 0, phi bar 0 is equal to 0, then SUSY is preserved at quantum level. Otherwise, if d of phi bar is always strictly positive, and it's not possible to find a configuration which makes it vanishing, then there is a SUSY, spontaneous symmetry breaking. But what I want to stress here is that there is a very precise prescription according to which you can study if you have in your theory SUSY breaking or SUSY preserved by looking at the derivative of the superpotential respect to the superfield and then evaluated. Since this expression for the potential energy is in fact nothing but F bar, because these are F bar, these are called the F terms. The F terms contribution to the potential energy. We will see that in a moment. Hopefully we get to that point. And then if we introduce now gauge fields, we will also have an extra contribution from some potential associated to the gauge fields that we will call D terms. But as long as we stick to pure chiral theories, only F terms can drive you towards, SUSY breaking or SUSY preserving. Okay, I think, yes. This is a good point to stop, because then I have to start with the gauge theories. Okay, so second and final part, sorry, let me switch off the light. This part. Okay, thanks. Okay, last part, as I promised, concerns the construction of n equal to 1 super-Yamnis theories, but I will primarily focus on the abelian case, as I said, just to the construction the same, So it's especially to be a little bit simpler. So n equal to 1, super Yang-Mills theories. Okay, so the idea is the same as the one that we usually study in ordinary quantum field theory, even not quantum. Let's stick to classical theories. We have a bunch of matter particles described by a bunch of fields, and these fields can be charged under some symmetry, global symmetry. Then I want to gauge the symmetry, and this implies introducing a gauge field in order to covariantize the derivative, and this leads to what we call the minimal coupling between matter and interactions. We are going to do the same. So basically, suppose that we have, let me consider for the time being a single chiral superfield. Maybe I didn't stress too much this point, but chiral superfields are definitely suitable representations, a suitable description of SUSY particle. Is there anti-chiral superfield? Yes, of course, chiral plus. When I say chiral, I always mean that there is the corresponding anti. Always, otherwise the theory is not real. Remember that phi has components 5 psi and f, and these fields can be in fact used to describe the dynamics of a spin zero particle. This can be used to describe spin 1/2 particle. Okay. Spin 1/2 particles are, matter particles. Therefore, chiral and anti-chiral superfields are suitable to describe matter. Okay, so we have sort of matter describing matter. Okay, we want to, as I said, we want to introduce interaction with, interaction mediator, so gauge fields. So suppose that the theory is invariant under U1 global transformation of the form phi, which goes into a phi prime, equal to e to d, something that I would call lambda phi. And, I want to promote somehow the gauge invariance to a super gauge invariant. So as you will see, but I'm just mentioning it now, but we will see it later in a deeper way. I can take lambda to be a superfield itself. Okay, and since the gauge transformation should not destroy the fact that I'm dealing with chiral superfields, remember chiral superfields are featured by this condition. Also, lambda has to be a chiral superfield. And of course, you have the same kind of transformations for the bar, for the anti-chiral, which will be, I can go a little bit down, which will be, phi bar e to the minus I lambda bar with d alpha lambda bar equal to 0. Okay. But then I want to make it local. So I want to gauge means that I want to promote lambda to be a function of the superspace, in particular the x coordinates. And so we want to gauge this U1, but preserving supersymmetry. Okay, I don't want to spoil supersymmetry, of course, while we are gauging a global symmetry. Okay, so if we have a situation where the commutator between a supersymmetry transformation and a gauge, this is gauge transformation, which now depend on X, do not commute, then the result on the right-hand side has to be necessarily a spinorial transformation, okay? Because here we have spinor transformation with the bosonic transformation, you will get something which is spinorial transformation, but something which depends on X, because now the gauge transformation brings into the game the X dependence. So you would produce something which is a SUSY transformation which depend on X. So you would produce something which is a local SUSY transformation. Okay. But the local SUSY transformation is a completely different story because this is supergravity. We don't want to discuss about supergravity. We want to keep SUSY global. We want to keep SUSY global. Therefore, the only possibility is that supersymmetry transformations and gauge transformations commute. Okay, but if they commute, this is just intuitive, just to grasp the idea. If they commute, then there are two nice consequences. The first one is that every single component of a superfield will belong to the same representation of the gauge group. So all the components of the superfield belong to the same representation of the gauge group G. Okay. Second consequence, which is basically a consequence of the consequence, you know that when we build up gauge theories, matter belongs typically to fundamental representation of gauge group, whereas the gauge field belongs to the adjoint. Okay. Therefore, since all the components of the superfield have to belong to the same representation, it means that matter fields and gauge fields cannot belong to the same superfield. Matter fields and gauge fields cannot belong to the same superfield or multiplet. The same thing. Okay. Therefore, this just to say that if we introduce phi, you know, the chiral field and the antichiral field, superfield to describe matter, I have to introduce another superfield to describe gauge fields. Okay. So we, in n equal to 1, we need two different superfields to describe matter and interaction. Okay, so matter, we said already that this is a chiral superfield. Interaction is what? We don't know. This is what we are going to build up now. Okay, so I will focus on the problem to find out a suitable superfield which contains the gauge field. And as I said, I will stick to the abelian case. So we are dealing with U1 gauge symmetry. Okay, so remember that in ordinary, I mean non-SUSY field theory, what you introduce to describe your electromagnetic field is F mu nu. F mu nu satisfies Bianchi identities. The rho F mu nu equal to 0, which allow you to express F mu nu in terms of the gauge field A. Okay. Now, first of all, we want basically to generalize this construction, but first of all, I need to remember, I need to translate into my double spin notation all what we know about F mu nu. So in double spin notation, I will not deal with F mu nu, rather I will deal with F alpha alpha dot beta beta dot, which is by definition, remember, sigma mu alpha alpha dot, sigma nu beta beta dot, F mu nu. Okay, but you can show, not you, but you can find in the books proof of that, that F alpha alpha dot beta beta dot can be always decomposed in this way as epsilon alpha beta, small f bar alpha dot beta dot, plus epsilon alpha dot beta dot F alpha beta. Just to say, you know, that when I'm dealing with a super field, rather than talking about F mu nu, as we do as usual, we will talk about these components F alpha beta and F alpha dot beta dot, okay? That are indeed symmetric components, okay? That's just to fix the notation. And in particular, one can prove that if you consider this combination, this is nothing but minus 1/4 F mu nu, which is in fact the kinetic term that you find in the pure gauge action. Okay, however, this is still ordinary case, simply redefined in terms of a double spin notation. Now I want to supersymmetrize the construction. Okay, so we now supersymmetrize this construction. Okay, and in particular, I want to write down something which looks like the supersymmetry version of Bianchi identities. This looks like, you know, out of the blue. I know it is out of the blue, but, you know, a posteriori, when you will find out what is the output of all my discussion, and then you look backwards, you will get convinced that this is the right thing to do, okay? And basically, the only consistent way to do. So in order to supersymmetrize Bianchi identities, so this will be SUSY Bianchi identities, we introduce a chiral superfield that I will call W alpha and the corresponding anti-chiral W bar alpha dot, and impose, and this is the analog of the Bianchi identity, impose that D alpha W alpha minus D bar alpha dot W bar alpha dot is equal to 0. This is what I think may sound a little bit out of the blue for the time being, okay? But believe me, this is the SUSY version of Bianchi identities. We will see later why. For the time being, just accept this condition. You can solve this condition. This is probably number 3. Solution to 3 is the following. If you write W alpha as D bar square D alpha V, where V is a real scalar superfield, and you write W bar alpha dot as D square D bar alpha dot V, then you can easily plug these expressions inside the Bianchi identity, and you will find indeed that this expression is identically 0. So this is a solution, okay? And V, being a scalar, real scalar superfield, has the usual expansion in components, the one that we know already. And in fact, you can write V as C plus theta alpha chi alpha plus theta bar alpha dot chi bar alpha dot. This is an expansion that we wrote already. Plus minus, let me put minus theta square M minus theta bar square M bar plus theta alpha theta bar alpha dot A alpha alpha dot minus theta bar square theta alpha lambda alpha minus theta square theta bar alpha dot lambda bar alpha dot plus theta square theta bar square D. Okay. Okay, and this is already something which makes me happy, because this is something that we note already. In the expansion of this scalar real superfield, I find a vector field A, which is, of course, what I will think of being, you know, my gauge field. And the rest of the components are the superpartners of this gauge field. Okay, but in order to prove that, you know, what I have written down makes sense, we have to reach the point where I will be able to write for you an action, and I will recognize that the action will be the usual QED action, not QED, just simply pure U1 gauge action, so minus 1/4 F mu nu F mu nu, plus the action for the corresponding superpartners. Okay, this is basically my way to proceed. Okay, but beyond that, of course, first of all, I have to tell you that this is a good construction, but where is gauge invariance? Gauge invariance in superspace can be formulated in this way. In fact, you immediately, no, I should write this as 4, and this is 5. Gauge invariance, with gauge transformations. How do you write gauge transformations? Look, I'm not dealing with matter now. I'm dealing with a pure gauge. Okay, so I want to write something which is the supersymmetry analog of a gauge transformation that would involve the gauge field. Remember, A mu goes into A mu plus D mu of something. Okay, I want to write something which is the supersymmetry version of this gauge transformation. The gauge, and remember, under gauge transformation, this is a good point to stress. Under gauge transformations, let me write here, gauge transformation, A prime mu equal to A mu plus D mu, give me a name for some function, sigma. under gauge transformations, and mu nu is invariant in the U1 case, okay? Keep this in mind. So I want to do the same in the SUSY case. I claim that the right gauge transformation is the following. V, so it is a transformation on V. V goes to V prime, which is given by V plus I lambda bar minus lambda, where lambda and lambda bar, as I said already, are chiral and anti-chiral superfield. Okay, why I'm happy with these gauge transformations? Because now you can immediately realize that W alpha and W bar alpha dot are indeed invariant under these gauge transformations, thanks to the chiral constraints on lambda and lambda bar. Okay, so W alpha and W bar alpha dot are invariant. Therefore, as you will see in a moment, if W alpha, W bar alpha dot satisfy the SUSY version of Yankee identity, they might be somehow related to F mu nu, which satisfy the Bianchi identity. Therefore, it is already a good thing that they are gauge invariant, because F mu nu is gauge invariant. Okay, let me write gauge invariant. Okay. The interesting thing is that what I have done here when I define the gauge transformation in this way is, parameterize the gauge transformation in terms of superfields. So these become indeed super gauge transformations. This is a very important observation. 6 are super gauge transformations. Why? Because if you take lambda, for instance, remember lambda is a chiral superfield. So lambda as a function of x, theta, and theta bar, remember, can be expanded into the lowest component, which will be a function of the famous x left, plus theta alpha, lambda alpha xl, plus theta square, lambda 2 xl. Okay, so now I put into the game more parameters of gauge transformation. Typically, the gauge transformation in the ordinary case is driven by a scalar function. Here, I introduce actually 2 scalar functions and 1 spinor function. So I have a transformation which is definitely much richer compared to the one of the ordinary case. Okay, now, one can write down the way, this is something that you can do. So basically what you should do, this is an exercise for you. What you have to do is to implement this transformation here in V, then you expand V and V prime in terms of their components. You expand lambda lambda bar in terms of their components. Let me see if I call them. Yeah, I use the same letters. Okay. This allows you to write down which are the transformations of the single components on V of V under this gauge transformation. Okay. How do they transform? So gauge transformations of components. Do it as an exercise. You will find the following transformations. If you look at the variation of the lowest component is basically V, let me call delta V to be V prime minus V, okay? And then you start computing delta C, which is nothing but delta V evaluated, which is nothing but I lambda bar minus lambda evaluated, and you will find I lambda bar 1 minus lambda 1. Good. you keep going, delta chi alpha, this will be minus d alpha delta v evaluated, and you find minus I lambda alpha. Delta m is equal to minus I lambda 2. Delta A alpha alpha dot is d alpha alpha dot lambda 1 plus lambda bar 1. Sorry, I have to write them because then I want to show you a nice feature of these transformations, and delta d equal to 0. Okay, let's keep this transformation. Then you have, of course, the transformation of chi bar, lambda bar, but let's look at these transformations. Since now I have many more parameters compared to the ordinary transformations, I could do the following. I could use lambda bar 1 minus lambda 1, so this gauge transformation, to gauge C equal to 0. We can set C equal to 0. I can use this gauge transformation for chi alpha to set chi alpha, and of course correspondingly chi bar alpha dot equal to 0. And then I can use this transformation to set m equal to 0. So I'm using lambda 2, and sorry, also m bar, of course, and lambda 2 bar, lambda alpha, lambda bar alpha dot, but for lambda 1, this is simply twice, minus twice I imaginary lambda 1, okay? So I can perform a gauge fixing exploiting the imaginary part of lambda 1, lambda alpha, lambda bar alpha dot, and lambda 2, lambda bar 2, okay, to gauge fix these fields to 0. This is gauge fixing. What I'm left with is the real part of lambda 1, because I didn't use the real part. And in fact, the real part of lambda 1 appears here. This is twice the real part of lambda 1. And this is exactly the kind of gauge transformation that I expect for my vector field, A alpha alpha dot. Okay, because the transformation is the derivative of a function. Therefore, I can basically identify the real part of lambda 1 with the usual gauge parameter. And, you know, exploit the fact that this superfield give me many more parameters to perform a partial gauge fixing. Okay, this partial gauge fixing is called the Guezzumino gauge. So what I found there, so setting okay, C equal to 0, chi alpha and chi bar alpha dot equal to 0, m and m bar equal to 0 corresponds to the Guezzumino gauge. And this is the gauge that you better use to simplify your calculations when you want to reduce a superfield action for gauge fields to components, but I will come back later to this point. Okay, note that setting these fields equal to 0 is equivalent to say that you are setting V evaluated equal to 0, D alpha V evaluated equal to 0, D bar alpha dot B evaluated equal to 0, and D square V evaluated equal to 0, D bar square V evaluated equal to 0. This is a rigorous definition of Guezzumino gauge. There is a subtlety, which, but I don't want to enter this because no, it's really very late. When you fix the Guezzumino gauge, you break supersymmetry in the sense that when you now perform a supersymmetry transformation, you go out the Guezzumino gauge. Therefore, you know, in this case, you have to apply supersymmetry transformations to get together with gauge, restoring gauge transformations. But okay, this is something that too technical, probably. We can skip this point. The main point that I would like to highlight is the following. Once you go to the Vezzumino gauge, and now we look at the independent components of W alpha and W bar alpha dot. Remember, they are chiral and anti-chiral superfields in the Vezzumino gauge. What we find is the following. W alpha, then for W bar alpha dot, you simply get the complex conjugate, has as independent and dynamic, not necessarily dynamical, independent components, has lambda alpha, which is W alpha evaluated. It contains F alpha beta, which is defined as the symmetric part of this tensor. Okay. And contains D, which is equal proportional to D alpha, W alpha evaluated. And of course, for W bar, you will have lambda bar alpha dot, F bar alpha dot beta dot, and D bar. Okay. But now I'm more than happy because I find this, let's say, the spinorial tensor F alpha beta and the corresponding F bar alpha dot beta dot that reminds me the decomposition of F mu nu. Remember that I wrote F mu nu as F alpha dot beta beta dot, and I said this can be decomposed into these two spinorial tensors. Okay. Good. So we are close to the right point, because now the last thing that I have to do, well, apart from the fact that I can, of course, try to recognize this two F as being part of an F mu nu tensor, what I have to do now is simply invent an action that, when reduced to components, reproduces exactly F mu nu, the ordinary one, plus, of course, all the extra terms for the propagation of, the super partners. And in fact, how do we construct an action? Pure gauge. Pure gauge action. You can work on it still as with an intuition, looking at the dimensions. Okay, I want to write something which contains, of course, A alpha alpha dot. The dimension of A alpha alpha dot is 1, fortunately. The dimension of V is therefore 0. And therefore, if you look back to the definition, the dimension of W alpha is 3 hub, mass dimension. Okay, therefore, if I construct something, for instance, like W square has dimension 3, and it is a very good object to be integrated on a chiral integral. Therefore, my proposal is that the action for pure gauge theory is the integral of D6Z of 1/2 W alpha, that is, plus the complex conjugate, of course. That is what we call W square plus W bar square. Okay, why this makes me happy? Because this is an exercise for you. If you go to component, how you have to do it? Well, you have to write this as the integral Then you have d2 theta, d2 theta bar. Remember, this is nothing but the derivatives. Let me put 1/2 outside. And then for W alpha, you replace W alpha with its expression in terms of V. Okay. And at this point, you start applying derivatives. Sorry, of course, this is not there. So this is not there. You start applying derivatives. And you evaluate at theta bar equal to 0. If you do the exercise, forget about the conventions up to factors in front. What I want you to check is that you will find this kind of terms. So this will be the integrals proportional to the integral of a number, forget about the number, an expression which is f alpha beta plus f bar alpha dot beta dot f bar alpha dot beta dot. Then you find, let me put the number, then you find another contribution with another number, which is lambda alpha d alpha alpha dot lambda bar alpha dot. And finally, another number. Let me move it a little bit. D square. Okay, but this is a very nice result because then I can recognize this to be -1/4 f mu nu, which is the usual pure gauge action for U1 gauge fields. This is a new term. This term is the propagation of the Majorana spinor, which is what? This is the super partner of the gauge field, and this is what we call the gaugino, in fact. And finally, we have this term, d square. You see, there is no derivative. In particular, there is no time derivative, so this is nothing but an auxiliary field. Okay. Good. This is for pure gauge. What I have to do now is to couple this theory, this pure gauge theory, to matter using a minimal coupling procedure. Okay, I hope now, if you, as I said at the beginning, if you now go backwards, you will find out that, you know, whatever I wrote at the beginning that looked like, you know, just out of the blue has a meaning, because in fact, what I end up with is what I would like to end up with. Okay, now how to couple to matters, coupling to matter. Matter, remember, is given in terms of a chiral and anti-chiral field. Well, the first observation is the following. Suppose that, of course, phi and phi bar are charged. So now these are charged and U1, in the sense that if I perform a U1 transformation, I can write something as I wrote already. And phi bar goes into phi bar prime equal to phi bar e to the minus I lambda bar, okay, where lambda and lambda bar are now the ones that I was considering for the pure gauge case, so they are covariant and anti-covariant parameter gauge superfield. Okay, let's take the kinetic term. The kinetic term, remember, is, as usual, phi bar. The question is the kinetic term gauge invariant? Let's see. Of course, the answer will be, what do you expect? The answer is no, in a very, even in a simpler way compared to the ordinary case, because if you now transform phi bar into phi bar prime, this will be equal to, let me write this, more amusing way, phi bar phi, this will be phi bar prime, phi bar, phi prime, which is equal to phi bar e to the minus I lambda bar, e to the I lambda phi. Of course, this is different from phi bar phi. So this is, the answer is no, it is not gauge invariant, okay? However, how can I make it gauge invariant? Remember that V transforms in the following way. And since we are abelian, this is equivalent to say that e to the V transforms into e to the prime equal to e to the V, put whatever you want, e to the I lambda bar minus lambda. Okay, therefore, if now I promote the kinetic term to be phi bar e to the V phi, let's see what happens. What happens is that when I move this to be phi bar prime e to the V prime phi prime, this will be equal to, you see, from phi bar phi transformation, I produce e to the minus I lambda bar minus lambda. From e to the V transformation, I produce e to the I lambda bar minus lambda. They cancel, and I do get the original term. So this is gauge invariant. Okay. And this is the supersymmetric version of the minimal coupling, because now inside, now if you write, so the new kinetic, it's not really only kinetic term, has to be phi bar e to the V phi, that can be rewritten as phi bar phi, which is the usual kinetic term for matter, plus phi bar e to the V minus 1 phi. I simply added and subtracted phi bar phi, which is equal to the usual term, kinetic term for matter, plus the sum for n from 1 to infinity of phi, well, let's put 1 over n factorial here, phi bar v to the n phi. So this new kinetic, which is not really only kinetic term, let's say the gauge invariant promotion of the kinetic term, contains the ordinary kinetic term for matter and an infinite number of interaction vertices. Interaction of, let's say, matter gauge interaction vertices. Okay. Okay. I'm really running out of time. So the only thing that I want to tell you is that, to conclude, the most general let me call gauge plus matter theory with n equal 1 supersymmetry, which is renormalizable, is of the form we have the integral of phi bar p to the v phi, the new, let's say, kinetic term, which is gauge invariant. Then you can still, sorry, then you have the pure gauge part. Remember, W, now I don't want you to mess up W, this is W, the gauge W, not the superpotential, okay? Plus D6 Z bar times 1/2 W bar alpha dot W bar alpha dot, okay, which is a complex conjugate. Okay, and then I can actually add some superpotential, but now let me call it P, not W, plus a complex conjugate, as long as this does not break, of course, gauge invariance. Okay, but in the U1 case, you can add another term, which is the following. This is still complete superspace integration times xi v. Okay, this is what people call the Fayet-Leopoulos term, which can be written, because it is gauge invariant, only in the U1 case. For U1 theories. Okay, last minute, this is really a final comment. Remember that when we were looking at, you know, pure chiral models like the Vezzumino model, I mentioned already a non-renormalization theorem, which concerns the superpotential. There is a second non-renormalization theorem in gauge theories, which is the following. Indeed, when you start doing calculations, perturbative calculations, you have to insert a coupling constant. So you can shift your V into GV. You can even put 1/g² here in front. Okay. And the second non-renormalization theorem, this time due to gauge invariance, not supersymmetry, is for GV. GV does not renormalize. So these theories enjoy, say, two renormalization, non-renormalization theorems. The superpotential does not renormalize. Here, I think in order to be consistent, I should now generalize the situation where you have more than one chiral. Otherwise, it's hard to define a P which is invariant. The superpotential does not renormalize, and the GV does not renormalize due to gauge invariance. So in this case, you have two things that constrain your theory: supersymmetry and gauge invariance. Okay, and this has very powerful implications for the renormalization properties of these theories. When you then move to n equal to 2, n equal to 4, you even have even more powerful constraint. Okay, this my time is over. Let me just mention that due to this, the combination, you know, of higher SUSY and gauge invariance, eventually implies that n equal to 4 super Yang-Mills, that probably you know already because this is one of the two main characters of the ADS CFT, n equal to 4 superreal means is finite. If you formulate the theory in superspace, you will never find ultra-value divergences. This is a finite theory. It is conformal. Okay, I think this is it. Time is over.